Good afternoon, children. We are going to study about the thermodynamics, that is +1 chapter. Already we have seen that the concept of thermodynamics. Today we are going to study about what is thermochemical equations. What is called thermochemical equations? Thermochemical equations. Thermochemical reactions. Thermochemical equations and reactions. Thermochemical reactions. This thermochemical reactions is nothing but it is the balanced chemical reactions. It is that balanced chemical reactions. Chemical reactions. This is to be balanced by this stoichiometric balanced equations. You know, stoichiometric balancing is nothing but you have to maintain this reactants. Number of reactants are equal to number of products. That is thermochemical equations. That is stoichiometric balance equations. But especially the thermochemical equations and reactions, or we can written some want to write these equations, we have to adapted some conventions. We have to adapted some conventions. What are that conventions we are going to adapted? The method of writing thermochemical equations. That's the first point. What is the convention we are going to adopt? The reactants and products. The reactants and the products, its coefficients are to be written as in this form of number of moles. And the second conventions which we are adopted, the reactions and its delta H value to be represented by positive value and negative value. That it is the meaning, just to please understand, I am going to write these equations. H2 plus O2 gives H2O. This is a chemical reaction. You write, this is 2 hydrogen and here that 2 oxygen. Now here 1 oxygen is here, you have to balance these. 2H2 plus 2H2O. Now this equation is balanced. Now the delta H is equal to minus 967.3 kilojoules per mole. Now here this negative sign indicates that reaction is exothermic reactions. The first point what it is stated, the reactants and products and coefficients to be represented as in a number of moles. You see here the 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water. Here these all molecules are gaseous molecules. These all molecules are gaseous molecules. And here this delta H value is enthalpy. This we have represented by kilojoules. That means it is a unit. So you please understand what are the convention. The first convention we have to mention the number of moles. The second convention we have to mention that whether the reaction is followed by this negative value or positive value, or it is to be that what is the unit we can mention. This also to be we have mentioned here. Everything we have to write according to these conventions, what is adapted for this writing methods of that thermochemical reactions. The third point you should understand that, you see here, if that reactions to be reversed, that means reaction reversed, the reactions to be reversed, that means the value also to be reversed, value also to be reversed. What's the meaning you should understand? In this reaction, if it is to be forward, and here that exothermic reaction, in this reaction, if it is backward, that it is endothermic reaction, the sign will become positive. This is a point, understand. So the reaction to be reversed, that means the reaction which is to be reversed, this to be reversed, that means 2H2O gives 2H2 plus 1O2, the delta H is equal to, that is plus 967.3 kilojule per mole. This is a point you should understand. The fourth point, what is the convention? The fourth convention, what is to be given our book? That is, if the reactions H2 plus O2 gives H2O, in this case, all to be mentioned the state, physical state, this is the physical state. The physical state is equal to, that the physical state is nothing but the substance to be gas, or the substance to be liquid, or the substance to be solid. We have to mention the gas to be in G with bracket, and liquid L to be in bracket, and S to be in bracket while you are writing thermochemical equations. The fifth point you write here, and what is the things you want to write about the thermochemical equations, whether it is endothermic reactions, or it is exothermic reactions, that we can understand by knowing this sign value. Endothermic means the delta H value to be, delta H is to be positive value. If it is exothermic, delta H is equal to negative value. So based on this only, we could understand about these thermochemical equations. Next, the things we are going to, that is that following that these are a convention point which we can adapted to that thermochemical equations to understand, and have to write, and have to learn this point of what is the thermochemical equations. Next, we are going to see what is the standard. What is the standard enthalpy? Standard enthalpy of the thermochemical reactions. Thermochemical reactions. Standard enthalpy. Chemical reactions. Standard enthalpy. What's the meaning of standard enthalpy? The standard enthalpy is nothing but the enthalpy. There is a heat change. The enthalpy is nothing but heat change. That is, we have written as H is the heat. Enthalpy change is that delta H change. Del means difference. The heat change is to be referred as delta H. Heat change is there. Now the point you should understand, what is the heat change? Enthalpy change is otherwise known as delta H. The standard enthalpy of thermochemical equations, we can calculate thermochemical reactions. That means that the heat change is occurred for the formation of 1 mole of the substance. 1 mole of the substance. 1 mole of the substance. That is that standard enthalpy formation of thermochemical equation, or any compounds. Enthalpy of formation of the compounds. Formation of the compounds. We can understand. So now you can take that one chemical reactions. What is there? It is also to be given our book. A moles of A plus B moles of B. Then it gives C moles of C plus D moles of D. There it occurs delta H value. Either it is positive or it is negative. Positive or it is negative. This is the concept. Now we can go for how to calculate this delta H formation of the delta H formation of any substances, delta H of the reactions or delta H of the reactions. If it is standard conditions, it is to be the 0 to be written as in this superscript. The superscript you have to write that 0. Now delta H formation of these reactions is equal to summation of, that is here summation of product minus summation of reactants. Summation of product, that means what are the products which are to be formed in this reaction, what are the reactants which are involved in these reactions. These formation values, each and every is having its own values. For example, you can take H2, that or else you can take there is to be the reactions C2H5OH alcohol. There you can take oxygen, that is O2. Now the product formed is called, we can write H2CO2 plus H2O. This is a chemical reaction. But what is formed here? Carbon dioxide is formed. What is formed here? H2O is formed. So for this, he is having one value, that is that formation of alcohol, which is also having this one value. It is also having this formation of that oxygen. Now the carbon dioxide is also formed and which is also having its own value. And these values ought to be, we can substitute here. And finally we can find these reactions. And there is to be delta H naught of the reaction is equal to. Now I am going to write this expanded form that you see here. Delta H naught of the reaction is equal to summation of, see what is that product here, C moles of delta H formation of C plus summation, that means we have to add it, summation, that is D moles of delta H formation of, that is delta H of the reactions of D minus, that you can write minus summation of, you can write summation of D, that is to be that reactant are A moles of delta H of H naught of A, that is plus, and B delta H naught of B. This is the point you should understand. Now this summation is equal to product, this summation is equal to reactants. Now from this value we can calculate delta H naught of the reaction is equal to, either it is to be positive value or it is to be negative value. This is minus, or you can write it as the minus value or the plus value, that is positive will be occur. Now in these cases, suppose that enthalpy summation, you take now this is for 10 joule and here for also you can write 10 joule and here you can take it as 20 joules of closures of there is that delta H formation of A, and here there is a 20 closures of delta H formation of B. Now in these cases they have to add these two. What will get 20? Here that's to be 40. Now you write that delta H formation of the total reaction is equal to 20 minus 40. That means delta H formation of this reaction is equal to minus 20 kilojoule per mole is a reaction, that enthalpy of these reactions. Now finally you can come to know this reaction to be negative value. So it is to be that exothermic reactions. So we can understand the standard enthalpy of the reactions by knowing this formula. You please understand very clearly, delta H naught of the reaction is equal to summation of the enthalpy formation of the product of C, the enthalpy formation of product of D, minus the enthalpy formation of the reactant A plus enthalpy formation of reactant B, and you have to add these all values. Finally you come to know and what is the enthalpy formation of the reactions. This is a simple concept. Next, the concept which we are going to see here, enthalpy of combustions, that is delta HC is nothing but enthalpy of combustions. Combustion is nothing but burning of any substances, that is we can write it as combustion reactions. Now you take for example, carbon is solid substance, is combined with oxygen to give carbon dioxide is a gas. The delta H is equal to minus 393.5 kilojoules per mole. You please understand. Now what has happened here? This carbon is burned in presence of oxygen to giving carbon dioxide. What are the things you should understand here? For what is the amount of energy which is liberated during this combustion of 1 mole of substances, 1 mole of substance, and which is producing 1 mole of carbon dioxide. This is a point you should understand. Without excess of air, the definition you should understand, 1 mole of the substance is completely burnt in presence of or without excess of oxygen or air. That produced compound or this concept we can write it as to be the enthalpy of combustions. The enthalpy of combustions. This is the example which is to be given. You can take for example methane also to be burned in presence of oxygen. This is also giving that carbon dioxide and plus H2O. And during this reaction, delta H is equal to minus 87.2 kilojoule per mole is the energy which is liberated. So this is also negative, it is an exothermic process. It is also negative, it is an exothermic process. Generally, combustions are exothermic process. All the combustion reactions are exothermic reactions. All the combustion reactions are exothermic reactions. Now this is the concept which we are going to understand about what is called as exothermic reactions. Now we are going to see that what is called as molar heat capacity. What is called as molar heat capacity. Now the point, what is that? Molar heat capacity. You should know the molar means there is a mass of the substance and mole of the substance, moles, number of moles, and mass to be, we can write it as kilogram. Mole we can write it as there is 1 mole of the substance, 1 mole, 2 moles. That is a point you should write 1 moles or 2 moles of the reactants. To be involving this process is nothing but we can say molar heat capacity. Now what is molar heat capacity? You take for example, there is a system. The system is nothing but it is an engine or anything we can take it as. Any system which is going to functioning. And this is the system which containing a fuel. If it is an engine which containing fuel or any of the things we can take it as any system, the system which containing molecules that you know, that is the molecules we can write it as mass of the substance or mole of the substance. We can take it here. Mass we can take it as 1 kilogram and mole we can take it as 1 mole. Now you take and here for this point, the system will absorb the energy. The system will absorb the energy. When it absorbs the energy, here that heat of the system will get increases and that is temperature. Heat and temperature will get increases. If the heat and temperature will get increases, what will happen? The kinetic energy will get increases. The kinetic energy increases. The kinetic energy increases, what will happen? Here the system is which is to be going to start its function, that is which is going to work. Now here when it is going to start its work after absorbing the energy, what's the amount of energy which is absorbed by the system? That is Q amount of energy is absorbed by the system. That is we can write Q is directly proportional to the mass what we have taken here. The Q is directly proportional to what's the temperature, what's the heat energy which is involving this process. That is directly proportional to delta T. Delta T is nothing but we can write it as T2 minus T1. This is the temperature differences from initial and final. This I is equal to initial, T1 is equal to initial and T2 is equal to final. That is the point you should understand. Now both you want to combine. Q is equal to, or you can write Q is directly proportional to M into delta T. Now you write Q is equal to C into M into delta T. This is nothing but proportionality constant, that is heat capacity, we can write it as. That is heat capacity. This is nothing but specific heat capacity. This is nothing but specific heat capacity. Now we are going to see this specific heat capacity by knowing this formula, that is Q is equal to C into M into, that is T2 minus T1. Now you see C is equal to specific heat capacity, that is Q, that is C is equal to, you write C is equal to Q by M into T2 minus T1. Now what's the things you should understand from here? C is equal to Q divided by M is equal to mass, and that is T and T2 is, that is nothing but temperatures. For this we can write it as its unit. Its unit we can write it as kilojoule, and M and its unit we can write it as to be kilogram, or you can write it as in mole. The temperature we can write it as in Kelvin. How to derive this unit? From this, C is equal to Q by, that is M into T2 minus T1. You write here C is equal to Q is kilojoule divided by, and unit derivations. Unit derivations. You write this unit derivations. Now in these cases you can write a kilojoule per mole. You can write it as to be kilogram. Here it is the temperature. Now these all to be, we can write it as kilojoule, kilogram, Kelvin inverse, kilogram inverse. If it is, the instead of this you have to substitute this mole substance. Now you can write kilojoule, and here it is that mole inverse, then Kelvin inverse. If there is a point you should understand here, what is called specific heat, the definition for specific heat, definition for specific heat. See, if there is that things you should understand, if you want to take 1 kilogram of the substance to be present in the system, 1 kilogram of the substance which is to be present in the system, now this to be the energy or the quantity of heat which is to be absorbed, the quantity of heat absorbed when rising 1 Kelvin of the temperatures. What is the quantity of heat which is absorbed, and what is the quantity of heat absorbed is called specific heat capacity. Is called specific heat capacity. If there is a point you should write, what is the definition for molar heat capacity? The molar heat capacity is nothing but, you can write, you see, if the substance to be taken in, the point you should understand what is called a molar heat capacity. The molar heat capacity is also defined, that is definition, defined. See, there is a heat absorbed by the 1 mole of substance, 1 mole of substance to rise 1 Kelvin temperature. That is that point you should understand. You see, 1 mole of the substance which absorb the heat to rise the 1 Kelvin temperature is called molar heat capacity. Molar heat capacity. The point you should write, specific heat capacity. Specific heat capacity. The heat which absorbed, the heat absorbed when 1 kilogram of substance, 1 kilogram of substance to rise 1 Kelvin temperatures, 1 Kelvin temperature. This is expressed as in this specific heat capacity. This is expressed as this molar capacity. The molar capacity and specific heat capacity, which is we can write it as to be the same thing, but it is to be the mole, it is to be the weight, that is the substance weight. This is mentioned in the mole concept. Now we are going to see what is called as the Cp and Cv. What is called as Cp and Cv? This is nothing but there is specific heat capacity at a constant volume. Specific heat capacity, we are going to calculate specific heat capacity. We are going to derive this, what is specific heat capacity. Now you write this, what is the specific heat capacity? Already I have derived here, Q is equal to M into delta T. That is the point you should write. Q is equal to, Q is equal to C into M into delta T. That is C is equal to, this C is nothing but we can write it as to be that Q by, that is M into delta T. And here M is equal to 1 and delta T also to be is equal to 1. In now these cases, C is equal to Q. That's a point you should understand. C is equal to Q when it is delta T is also 1 and mass also to be 1. Now in these cases, the heat capacity is equal to the heat absorbed by the system. This is a point. And here we are going to compare how to derive these concepts without work done. How to calculate this Q value by using work done. And here, according to the first law of thermodynamics, according to law of thermodynamics, according to first law of thermodynamics, you know the concept, what is that first law of thermodynamics? There is a point you should understand. And here if it is in a system, you consider this is to be the system. And if the system is absorbed that energy, that is it is a gain to the system, now we can represent it as a plus. If the system is liberating that energy, now we can write it as a minus Q. This is quantity of heat absorbed by the system, quantity of heat liberated by the system. And here by this absorption, what will happen? This is all to be associated with the molecules are present inside. Now this will produce a kinetic energy, and which is the molecules are moving from. That is the point you should understand, already I have studied. And here because of that the system is going to done the work. If the system is going to done work, and here in these cases we have to write work done by the system, it is lost to the system. So now we can write minus W. If the work is done on the system, we can write it as a plus W. This is a point you should understand. According to the first law of thermodynamics, U is equal to, U is nothing but internal energy. Internal energy. U is equal to, that is the point you should understand, Q minus W. U is equal to Q plus W. U is equal to Q plus P delta V. U is equal to Q minus P delta V. All are same. This is also work done. This is also work done. Why we can say work done? Because P delta V, that means volume is changing, that is V2 minus V1. If the system is going to done the work, what will happen? That it get expand. That is expansion. The system is undergoing expansion. Volume will get increases. Volume increases. In these occasions we can say that because of this expansion, the system is undergoing working or it is undergoing work. So that we can refer as work done by the system is referred as U is equal to internal energy of the system. Only define this to be the work done. That is U is equal to plus P delta V. And here this P delta V is nothing but we can say work done. W also nothing but we can say it is work done. Now we are going to see here that is U is equal to minus Q minus P delta V. It is also explain this work done by the system. Work done by the system, work done on the system, plus is done on the system, minus is by the system. That is, it is also evaluated as a work done. From these work done values, we are going to calculate what is that Q. Now you see here, there is that point you take now in this equation. U is equal to, there is Q minus P delta V in this case. Q is equal to P delta V. Now what is the Q you can understand. Already we have derived as Q is equal to C. This is a point you should understand. Now you take this Q is equal to, there is a point what you can say, U plus P delta V. U plus P delta V. Now you have to differentiate this equation. Now you have to differentiate this equation with respect to this volume, constant volume. The volume to be constant. That you have to differentiate this equation with respect to the time. This is a point. Sorry. That you have to differentiate the equation with respect to temperature. Now I differentiate these equations, that you can see dq by dt is equal to du by dt. This is a point you should understand. Du by. And here there is a volume to be in constant. Now this is the point you should understand. That du is equal to dq by dt is equal to, that is temperatures. That is temperature. T capital temperature. Now this is equal to du capital U by dt. This is equal to du by dt is equal to Cv. We can say constant volume. C for heat capacity. Now you write Cv is equal to du by dt. This is that derivations. We can get it from this. The same concept what we have studied there in this case of first law of thermodynamics. The second there is a derivations which is to be explained this first law of thermodynamics. There is He is equal to U plus P delta V or PV is the formula. You know that. That you can write delta H is equal to delta U plus P delta V. This is a formula. This is also the first law of thermodynamics. First law of thermodynamics. Delta H is nothing but enthalpy. You know that. Change. This is nothing but internal energy change. Energy change. This is nothing but pressure of the system. This is volume change of the system. Volume change. Now you take this, and here if it is an ideal gas, you know that if it is an ideal gas, the ideal gas equation is equal to PV is equal to nRT. And here also we can calculate the PV is also, we are referred as to be, this is the work done. This work done is equal to nRT. Now you take these equations, in these equations, that is you can write H is equal to U plus P delta V, that is nothing but work done. You have to substitute these PV values or PV, nothing but H is equal to U plus PV. This is otherwise known as H is equal to, there's a point U plus PV is equal to, that is nRT. You write nRT. Now you have to integrate, differentiate this equation, not integration, you have to differentiate this equation. While you are differentiating with respect to T, differentiate this equation with respect to temperature. Now what will happen, this differentiate equation, that is delta H by delta, that means dou H by dou T is equal to dou U by dou T plus N or dou T by dou T. This all cancel, you will get the values of that, what is it? Dou H by dou T is equal to dou U by dou T. This is equal to, this is plus with that N or, the point you should understand. Now this is equal to, already I have given, This is U equal to, that is dH by other dou H by dou T or del H by del T is equal to, we can write Cp. And dou U by dou T is otherwise delta U by delta T is equal to Cv. Now this is a point you should understand. And Cp also we have derived and Cv also we have derived. And from this equation, suppose the point you should understand, the number of moles, what is involving? N is nothing but number of moles. This is gas constant, you know that it is a gas constant. From this relationship, we have to take these equations now. Here you take it now. The point what is here? Dou H by dou T is equal to dou U by dou T is, that is plus NR. You write now. This is otherwise known as Cp is equal to Cv plus NR. Now you write Cp minus Cv is equal to NR. This is why it is having greater value. It is having greater value. Why? Because now you take and you consider this is a system. The system which containing molecules, you know that, and which is having kinetic energy, you know that. The temperature will be rise. The temperature will get rise. And if the temperature will get rise, you know that apart from that and surrounding, apart from the system, which are called as, we can say, surroundings. So the system is going to work done against to the surroundings. The system is going to do the work against to the surroundings. At that time, the temperature will get rise, and here, there we can say the volume to be constant. In that occasion, what will happen? The Cp value is greater than and Cv value. Now, the Cp value is greater than Cv value, that is Cp minus Cv is equal to, we can write as NR. This is otherwise known as Cp by Cv is equal to gamma for the ideal gases. For the ideal gas, you write this Cp by Cv is equal to gamma. This is the derivations which we are going to understand about what is the relationship between Cp and Cv.